Hi everyone, welcome to our next unit. This unit is called Solutions, and we're going to start off our unit by learning about the structure of water here. So solutions, of course, often involve water. If I asked you to make a solution of something, it would often involve water. So that's why it's important for us to learn about water and how it works, really. So water is what's called a polar molecule. Oh, one thing I was going to mention, make sure you're taking notes through this, okay? So water is what we call a polar molecule. This means that it has a positive end and a negative end. So if you look here, this red ball here, this is our oxygen atom. These two are hydrogen atoms here. Now, when they bond like this, they bend and they end up in this bent shape like this. And that's because of the charges here. So we end up having a slightly negative charge around the oxygen side. So this part of the water molecule is slightly negative. The hydrogens are slightly positive here. And then that causes water to be sticky. Now, this is one of those things where people are like, yeah, you're crazy. Water is not sticky. What are you talking about? When my hands are sticky, I use water to make my hands not sticky. But if you imagine, or you can, just imagine it. You take a little bit of water in your hand and then turn your hand upside down. So if you put your hand upside down, what happens to the water? Yeah, it drips to the floor, right? Or the counter, whatever. However, does all the water, or is some still stuck to your hand? And yeah, your hand is still wet. It doesn't automatically become dry. So this shows us, this is a good example of how water is sticky. The water is actually sticking to your hand. So water is sticky because of these things here, the weak hydrogen bonds. So again, this is negative, that's the oxygen part, that's the hydrogen, oxygen, hydrogen, oxygen, hydrogen, and that would continue, that pattern would continue throughout the molecules. But if you look here, what do we know about opposite charges? Opposite charges, opposites attract, right? So we know that positive and negative charges like each other. So if we look there, that's why these are attracted here. Because those positive and negative charges from different molecules are attracted to each other, and we call those weak hydrogen bonds in chemistry. It also, because water is sticky like this, or water is a polar molecule, it allows us to bend water. And again, this seems kind of weird, right? Bending water, what are you talking about? So lucky for you, I took a little video of myself bending water. So we'll watch it. Hope the volume works okay. Anyways, this is my kitchen sink running. So right now I'm going to comb my hair. So you're going to take a comb, you're going to comb your hair and build up some static. And then you're going to bring it near the water. So watch what happens here. Woo, there we go. Woo, look at that. It's magic. I am a water bender. So as you can see, the water is bending, and I'll go back to the video. I was gonna say your teacher, so me, so I can explain how it works. Okay, so yes, you are a water bender. That's actually a really fun demonstration to do if you have any little kids around. I know I did it for my sons when they were little, and I told them that I was a water bender, and they were really impressed by me. So I recommend it. It's fun. But seriously though, try it out. Just make sure the stream of water is a thin stream of water. Okay, so let's talk about why that happens. So we've got our droplets of water here, and we've got our comb. This is my comb here. Beautiful illustrations. Now, when you comb your hair, what happens is the electrons from your hair get stripped off and deposited on the comb. So that happens through friction. And that's one way static electricity is harnessed, and you would have probably gone through that in grade 9 science. So because the electrons are taken, we should give this person eyes. Because the electrons are taken and deposited on the comb now has a negative charge. Now, what part of the water molecule then is going to be attracted to those negative charges? Yeah, the hydrogen part. So the positives that come from the hydrogen atoms are going to be attracted to that negative comb, and that's why you're going to see the water bend towards that. So because of water's polarity, you can actually move it that way using magnets. All right, I think that's really cool. So why is water polar? So it has to do with something called electronegativity. So make sure you know that term, electronegativity. This is an atom's ability to attract electrons. So basically, it's like, how much does an atom love electrons? That's electronegativity. Now, in terms of the periodic table, there is a trend, and electronegativity, generally speaking, is going to increase as you move upwards and to the right. So as we move upwards and to the right, you're going to get higher degrees of electronegativity, which means those atoms like electrons more. So if we look at hydrogen and oxygen, and this actually has values on it. Hydrogen has an electronegative value of 2.1. Oxygen has an electronegative value of 3.5. So what that means is when you've got oxygen bonded with the hydrogens, the oxygen likes the electrons more. So these are covalently bonded here, which means they're sharing their electrons. However, the electrons are going to spend more time around the oxygen atoms because the oxygen atoms likes them more. And the hydrogen atoms, they also like electrons, but not as much. So that's why these are going to have a slightly positive charge. It's not a full charge, so you wouldn't ever say, yeah, that's why we call them partial charges. I'm actually use this Greek symbol here to indicate that usually. So we've got a partial positive charge on the hydrogens, partial negative charge on the oxygens. And that's because it's covalently bonded, and it's because of electronegativity. Now, we're going to go through the solution process. So this is basically how things dissolve. So this is how things dissolve. So basically, ionic and covalent molecules dissolve things differently. So just as a review, covalent molecules, they're going to share their electrons. For the most part, they're from the right side of the periodic table. So these are my nonmetals. Whereas ionic compounds give and take their electrons. So those are from opposite sides of the periodic table. So this would be a metal and a non-metal bonded together. So shared electrons here. Sodium giving an electron to chlorine. That's a good example. That's our salt here. That's a good example of an ionic compound. Now, how these two things dissolve, or two different types of molecules dissolve, are different, and we have to understand how that works. So I had some really cool animations, and then I realized that you cannot run Java on an iPad. Who knew? And I only have a house full of Mac products, so I couldn't do it. So I'm going to draw it out for you. So we're going to first go with ionic. So, ionic. Let's use sodium chloride as our example. When sodium chloride gets put into a solution, so let's dump salt in. So if we took a salt shaker and we shook it and we put it in a glass of water, what would happen to the salt? It would dissolve. Now, what ends up happening, how that dissolving process works, it's called the solution process, is that the sodium chloride actually dissociates. So it's going to break apart into Na plus and Cl minus. So it's going to break apart into its ions. So if we took a snapshot of it, look at me, this is a magnifier here. We'd have Na plus and Cl minus moving around here. And we'd have different ones. So we'd have, so the Na plus and the Cl minus would separate. Now, one thing that people kind of mess up on is they say NaCl breaks apart into sodium and chlorine. Well, that's not true. Remember, the ions matter, so those charges make a huge difference. So it's going to break apart into its ions here. So when that happens, the water molecules are going to surround those ions, and that's why it dissolved. It sort of goes into the water, or it dissolves into the water. So how that would look, if we have sodium, for example, it's got a positive charge, so water is going to line up around it, but it's going to line up around it so that the oxygen is close, because what do we know about the polarity of water? That's a negative charge there, right? So we've got oxygen atoms there, or sorry, the oxygen part of the molecule is going to line up around that sodium atom, because opposite charges attract, and the negative part of the oxygen is attracted to the positive part of the sodium. Now, if we want to look at the chlorine, the opposite is going to be true. So now the water molecule, what part of the water molecule is going to line up around it? Yeah, the hydrogens. So we're going to have our hydrogens. They're positively charged, or partially positively charged, so they really want to get near that chlorine. So we've got our H's. And you draw more in there, right? So this is how the solution process works. So the water molecules surround the ions, and they orient themselves so that the charges are always the opposite charges attract. Okay, so that's ionic. Now we're going to take a look at covalent. Okay, so for covalent molecule, let's look at sugar. So C6H12O6. Now, if you put sugar inside your... Let's have a little mug. If you put sugar inside your teacup into your hot water, what's going to happen? Again, it's going to dissolve, right? You're not going to see the granules of sugar there. So what's going to happen then? The sugar, so this is in a solid form here. Does it break apart into carbon, hydrogen, and oxygen? No, it does not. So covalent molecules do not ionize, but they will change state. So it started out solid here, and then it goes to aqueous. So aqueous, that's what that AQ is. AQ, and that means aqueous. What that means is it's dissolved in water. So if we take a snapshot of that, let's blow it up. So what's going to happen then is you're going to have, sorry, C6H12O6, all these sugar molecules around here. They are not going to dissociate, but they're going to separate from each other. So say you had a sugar cube or something. It's not going to stay in that form, obviously. All the different particles are going to separate from each other. And then the water will orient itself around, but because the charges are not, the charges of the sugar are not very strong, the water's just going to orient itself around there, and you don't need to worry about the charges. It'll just surround it. So in both cases, the water molecules surround the species as they're in the solution. But of course, the main difference is in the ionic, it's going to break apart into the ions here, and then the water orients itself around there, versus the molecules where it stays in its molecular form, just changes state. So it moves from a solid into the aqueous state. Okay, so that is the difference between both of them there. Now, dissociation. So just some terms. I mentioned this before there. So this is when the ions are going to separate from the crystal structure. So when you've got a solid, so we write dissociation equations like this. Now pay attention to the states here. So this would be silver chloride. So it starts out as a solid, and then it's going to break apart into its ion. So it's going to ionize into Ag plus and Cl minus. So you may need your periodic table if you're unsure of some of the charges of these, and you'll figure it out that way. So breaking apart or ionizing, dissociating, those things all mean the same thing, into their ions. So again, do not forget the charges. Those charges are very important, okay? You can't leave them off. So let's work through another example here. So let's say we had sodium sulfate. So sodium sulfate is going to start as a solid. So when it dissolves, it's going to combine with water. So you're dumping this into a glass of water, say, or a beaker of water. So sodium sulfate starts out in the solid. When it ionizes, it's going to become aqueous. So that means the water molecules are going to surround the ions and it's going to dissolve. So we're going to break it apart. So first of all, we've got sodium, so Na+, and then my state is aqueous. And then I've got SO4 2-, and that's also aqueous. Now, you're not done though, because what do you always have to do for every chemical equation? You got to balance it. So I need a 2 there. So this is the dissociation equation for sodium sulfate. Let's do another one. So lithium phosphate. So Li3PO4 starts out as a solid. It's going to break apart. Lithium, when it ionizes, is Li+, so lithium+, plus the phosphate ion is PO4 3-. And again, I need to balance it. So I need a 3 there because I had 3 lithiums over here. Now, I can't forget my states though. They're definitely part of that. Okay, so these are dissociation equations here. Oh, I wrote all over that. Hold on. Oh, there we go. Solvation. So solvation, a couple more terms here. Solvation is the process of surrounding the solute ions with the solvent molecules. So remember when we had like the Na+ and then the water lines up around it by bringing the oxygen close? That is solvation. Not to be confused with salvation, which some people do. We're not going to church. So solvation is when the water lines up around either the ions or in a molecular compound, the compound, for it to dissolve. So hydration. So when this is when the solvation process involves water as the solvent. So you don't, not everything is dissolved in water. You can use other solvents, but when it is water, we call it that something would be hydrated, okay? So when the solvation process involves water, the solute ions are said to be hydrated. Good. Now, heat of solution. Not too much more here, guys. Energy is required to break attractive forces. Therefore, the separation of solute particles from one another and the separation of solvent particles are endothermic processes. They use heat. I feel like maybe I should just quickly review solute versus solvent. Solute is dissolved. So this would be our salt or our sugar. Solvent does the dissolving. So in this case, it would be the water, right? So that's the difference there. So basically solute, if you've got like a sugar cube, those particles, when they separate from each other, that's going to take energy. So that's an endothermic process because it's using energy. The attraction between the solute and the solvent particles is exothermic. So that's going to release energy. So the heat of solution, this is also sometimes called enthalpy. The heat of solution is the net energy change, okay? So energy absorbed greater than energy released, endothermic. If the energy absorbed is less than the energy released, exothermic. So endothermic, it's going to feel cold. Exothermic, it's going to feel hot. Okay. Your assignment is, if you've got the assignment booklet already from the school or if you're printing it yourself, exercise 44, questions 1 to 10. So that's what I would like you to do. I'm not going to make you do the second part of it here because you basically just copied it down in your notes anyways, so we're not going to worry about that one. So this one, oh wait. There we go. So exercise 44, questions 1 to 10. So I'd like you to write those down. I wouldn't recommend well, you can if you want, but I find it a pain to write type chemistry equations. They're very problematic with superscripts and subscripts. Anyways, handwrite it, take a picture of me, you can hand it in on Schoology, and that will be due, well, in a couple days. So I'll give you 2 days to do this, and then I'll put it on Schoology for you. Okay, that's it tonight. Thanks, guys.